Okay, let's continue the analysis of variance. In last week, we mentioned what is the ANOVA for the adaptive model. We already know how to calculate the sum of square for the main effects and the total sum of square. And this is the equation we are going to use. When we calculate the total sum of square, we can use this equation. And this will be the summation of the main effects and the sum of square due to error. Therefore, as I mentioned earlier this morning, when we want to, how do we calculate the degree of freedom for the error term? We can use this equation. The degree of freedom for sum of square will be the total degree of freedom, which is the experimental design, number of experiment in the inner array minus 1 will be the total degree of freedom minus the model, which is the main effect, maybe some interaction effects if you want to calculate the interaction effects in the future. And the rest of that, when you minus the sum of square due to the model, you can get the degree of freedom for the error. As I mentioned, the total degree of freedom will be the number of experiments. For example, if you are using Ln orthogonal array, the degree of freedom for your system, for your experiment, will be n minus 1. Similarly, for the sum of square due to error, you can use the total sum of square minus the sum of square due to the model, due to your model, including the main effects and some important interaction effects. And we will talk about how to calculate the sum of square due to interaction later. Then, the reason we want to use ANOVA is we want to understand how important each effect is. So we want to calculate, we want to estimate what is the significance. And the significance is, in the word, is similar to importance. So this significance is similar to importance. So in Taguchi, he will propose a method called percent contributions or contribution percentage to estimate how important or how significant for each effect. But in traditional experimental design, they are using F-test. Depending on how much time we have, if I have more time, I will talk about F-test. Otherwise, we just talk about contribution percentage to be a tool to estimate how important for each factor. So here, let's using example. So we talked about last week, sum of square for each main effects can be estimated using this equation. As an example of L18, just like our quiz before the class, if your factor has 3 levels, for in L18, each factors will repeat it for 6 times, right? Because 18 experiment, 3 level. Therefore, each level will repeat 6 times. Then M will be 6. So the sum of square will be the main effects, A1, A2, A3. And A1, A2, A3 can be calculated using the average output minus the total average. The main effect square summation, which will be that, then you can get the main effect for A. And sorry for the missing word. So because this sum of square will due to the change of each factors. And in this case, factor A has 3 levels. As I mentioned before, for 3 level factors, the degree of freedom will be 2, which means that they need to have 2 variables or 2 values, 2 comparisons. Then we can determine whether factor A is big or small, right? Just like the tree, we want to find out which tree is the tallest. We just need to make two comparisons. Then this sum square is due to that two comparisons. So when we want to calculate the average sum square for the factor A, which we call it mean sum square, which is the sum square due to A divided by the degree of freedom. If factor A has P level, then the degree of freedom will be P minus 1. In our L18 example, A is 3 level. Then the degree of freedom will be 2. So the mean sum square due to A will be sum square of A divided by. Similarly, for if it is L8, then each factor will have 2 minus 1 degree of freedom. And in this L8, each factor will appear 4 times. So when you calculate sum square due to A, this M, the repeated time, the repetitions in the experimental design for each level will be 4 times, right? L8, 4 of the experiments, A is set in level 1, 4 set in level 2. This is how you calculate sum square due to A. And then you can calculate the total sum square. As I mentioned before, how do you calculate the error sum square? The error sum square will be the total degree of freedom, total sum square minus the model sum square. In this case, if you have A, B, C, D, E, many effects and no interaction, then the error sum square will be the difference. And we have using these experiments, these samples in last week. So you can find out the degree of freedom, the sum square, and the mean sum square will be the sum square divided by the degree of freedom. Okay, A, B, C, D, E, in this case, they are the same because the degree of freedom is 1. So when divided by 1 will be the same. But as you can see, the error mean sum square will be this number divided by 2, which is 0.376. It's different from the sum square, right? This is how we calculate the mean sum square. And now we want to show you how to calculate the sum square due to interaction. And the sum square, first we need to find out what is the degree of freedom for interactions. As I mentioned, the degree of freedom for two factors interaction will be the level minus 1 for each factors, and then multiply by these two factors. N minus 1 multiplied by N minus 1, right? So this will be the degree of freedom for interactions. And first, when you want to calculate the sum square for this interaction, before the calculation, you need to make sure, I'm making red, you need to make sure this interaction can be estimated, right? Before the calculation, you have to make sure this interaction is estimable. What does it mean by estimable? Because we are using fractional factorial, you know that the arrangement for each factors will influence the confounding structures. So in the confounding structure, some main effects will confound with the interaction effects. If the main effect is confounded with your interactions, or certain interaction is confounded with other interactions, then this interactions is not estimable. Which means that when you analyze the sum square, which is confounded, which is mixed with the other confounded effects. So when you estimate sum square due to A plus B, it doesn't give you a correct number. So before you do the calculation, you have to make sure, you have to look at the confounding structures, make sure that your interaction is estimable. Okay, we will show you later. Once it is estimable, then the calculation can be used, can be measured using either this equation or that equation. Okay, these are the same. By using some simple calculation, you can change this one into a simple equation like that. And the concept just like what I introduced before, which is the kind of effects, interaction effects, right? Due to different combination. This is the different combination A, B, and minus the total average. This difference is due to the combination of A and B. And you sum up all the interaction effects kind of, and multiply by the repeated number when you calculate the average of this combination. And this has to minus the sum square due to the original A and B. The difference will be the interaction sum square. And this can be simplified using that equation, because this one you can easier using the equation we show you later, the Excel equation to calculate. Right. So it will be easier just using an example to calculate. So here, this is the equation we are going to use to calculate the sum square due to interaction AB. And the mean sum square will be divided by the degree of freedom for this interaction. If A is label MA, B has label MB, so the interaction, the degree of freedom for this interaction will be MA minus 1 multiplied by MB minus 1. So the mean sum square will be the sum square divided by degree of freedom. Instead, look at the screen that's using Excel to do the practice. So please open last week's file. Hopefully you still save the last week's file. If you forgot, give you 5 minutes, you can recreate the last week Excel file. Okay, last week we have calculated this example, just like what we showed you before. And the result will look like this. Okay, this is the result we calculated last week. All right. So here in last week, we only consider the main effects. So the model is, as you can see, if we only consider the main effects, the model will be the mu plus AI, BJ, CK, D, say D, E, M plus L. This is only main effect. And this week, by using the same data, we want to consider if there is any interactions, right? This week, we want to consider interaction. Just like what we said, we want to consider the interaction. We have to make sure first whether this is estimable, whether the interaction is estimable. Let me see. Okay, I want to copy the number over so we can do that here. Okay, so please retrieve the file. Let me correct it a little bit. All right, this is where we were last week. And we can calculate the degree of freedom for total degree of freedom will be, since it's LA, the total degree of freedom will be 7. Right, so the L degree of freedom will be the total degree of freedom minus the degree of freedom for your model. Right now it's 2. We didn't consider this interaction in last week. We will later, right? So here, again, the total sum square will be, just copy the last week's number. The total sum square will come. Okay, let me calculate again by myself. The total sum square will be the sum square for the output minus total number will be 8 multiplied by average square, and this will be total sum square. So here the sum square due to error will be the total sum square minus your model. And the mean sum square will be the sum square divided by their degree of freedom. So this is where we were last week. Yep. Let's make it 3 digits, so it will be the same as our class notes. Any questions? This is where we were last week. Now we want to estimate the interaction D and E. D and E. Before we estimate the interaction sum square for D and E, we have to make sure this interaction is estimable. How to make sure whether it is estimable or not? We need to check their confounding structure. So here, let's find out what is the confounding structure. What is the confounding structure? Let's see. Let's put it down here because let's put it down here. This is how we arrange our experiment, right? And this L8. So we need to find out the confounding structures. Let's look at the class note. How to find out the confounding structures? There's a interaction table. Interaction table where we were, this one. For L8, the interaction table is this one. So once we arrange our factors in L8, we can use this interaction table to find out the confounding structures. So now it's your turn to find out what is the confounding structures for this arrangement. Let me see if there's an answer here. For this arrangement, the confounding structure will look like that. But in our case, our confounding structures will be different. Okay? Different arrangement will have different confounding structure. We have tried that before. So the confounding structure of this one will be different from that one. As I mentioned, they will have a different resolution. Remember? Resolution 2, 3, and 4. How about our experiment? What is our confounding structures? Let's put it here and try to find out confounding structures. Now, we have 5 effects, A, B, C, D, E. So from this table, please find out the confounding structure. How to have the, first we need to find out how many interaction will be. We have 5 effects, right? A, B, C, D, E. So there will be C 5 by 2 10 combination, right? 5 effects. Every 2 combinations will be combination 5 by 2, which is 10 combinations. How to have this 10 combination? We can start from A, AB, AC, AD, AE. Next, come to B, BC. We don't need to start from A because BA already here. AB is the same interaction as BA. So we don't need to go back. We just follow B, C, B, D, B, E. Next, come to C, C, D, C, E. Finally, D, E. Total 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 two-way interactions. But we need to find out where this interaction will be in our experimental design. This is our experimental design, right? So let's put a confounding structure here. I will check one for you. Where is AB? AB, we are putting 1 and 2. You have to look here, 1 and 2, right? Let me copy this interaction table over so we don't need to change from one table to another, right? Put it here. And you can look at your class note. So we need to find out confounding structure. Where is AB? Column 1, column 2. The interaction of column 1 and 2 will happen in column 3 here. So you will see AB will confound with column 3. How about AC? 1, 3. I'm sorry, 1, 4, right? A is column 1, C in column 4. So interaction AC will be 1, 4 will happen in column 5. AC. AD 1, 5, 1, 5 in column 4. AD. How about last one? AE. 1, 6, 1, 6 happen in column 7. AE. Right? So you finish this 4. Continue for the rest. You will finish the confounding structures. Where is B? BC. How did you do that first? Because we need to analyze what? We need to analyze DE. Where is DE? DE, D in column 5, E in column 6. DE will be 5 and 6. 5 and 6 happen in column 3. All right? So you can see DE is not independent. They are confounded with another interaction AB. All right? So I'll let you finish the rest. Then you can have the confounding structures. BC will be 2, 4. 2, 4, and 6. Okay, I believe you can finish the rest. Any questions? How to find out the confounding structures? Please don't copy the structure directly from the screen. You need to find out by yourself from the interaction table and the arrangement of the selection of your columns. You will be able to come up the confounding structures. So from these confounding structures, you will see what is the resolution. What is the resolution for this experiment? Is it resolution 3, 4, or 5? I will ask you in the test 2, what is the resolution? Resolution 3, resolution 4, or resolution 5? Which one? You need to go back the definition of a resolution. This will be resolution 3. Since main effects are confounded with interaction effects, so this only have interaction 3. Therefore, we shouldn't be able to estimate the interaction effects, because if there are any significant or any important significant interaction, will make the estimation of the main effects biased or incorrect. Therefore, there will be some assumptions. Therefore, if your interaction effects need to be estimable or can be estimated correctly, the assumption will be has to be negligible. Because A is confounded with CD, B confounded with CE, these interactions has to be negligible. Otherwise, your estimation of main effects will be incorrect. We can check that later. But now, if we want to, as a practice, if we want to estimate the interaction of DE, here DE confounded with AB. So if you want to estimate the interaction of DE, the assumption is AEB interaction need to be negligible. Okay, so this is very important. When you want to do the analysis for the interaction, you have to check the confounding structures and understand what kind of risk when you estimate the interaction effects. First, you cannot estimate the interaction effects which confounded with the main effects. So if you want to do the interaction analysis, you have to make sure that the confounding structures show that interaction can be estimated. Here, since this interaction, CD, C, B, AC, BC, and BC, they are confounded with the main effects. Since they are confounded with the main effects, they cannot be estimated. Okay, make sure this interaction cannot be estimated. They cannot be estimated. Since when you estimate the interaction effect for CD, which means that CD confounded with A, so your sum square due to CD, which will be mixed with sum square due to A, they cannot be separated. Okay, they cannot be separated. So if you calculate CD, which will be incorrect because you're already using the sum square to estimate A. Then this is why the assumption that this interaction has to be negligible. So if you look at some paper, they analyze the interaction CD. If the arrangement is like that, you will know the analysis of this interaction or the ANOVA will be incorrect. The only possibility that you can estimate the interaction will be AB, D, or AE, BD, because this four interaction doesn't confound it with interaction. Even so, if you want to estimate the DE, since it is confounded with A, B interactions, so you can only estimate one of that, either D or AB. If you want to estimate DE, the assumption is AB need to be negligible. Any questions? This is very important before you do the ANOVA. All right. So as you can see, you can do these confounding structures and make sure your assumption before you do the analysis of interactions. ANOVA for DE. All right. Let's assume it is estimable. Then let's try to estimate how to estimate the interaction DE. First, just like what we did before, we first want to come up the interaction plot. The interaction plot, we need to have this combination, D and E, and calculate the average output for each combination. All right, as a practice, you should be able to get the interaction plot or the combination of DE. DE will be here. So 1, 1, which is this one, and that one, right? Because DE is 1 and 1 for this experiment number 1 and experiment number 8. How about 1, 2? I'm sorry, 1, 2. D level 1, E level 2. D level 1, E level 2. You can find out this experiment is like that, and also this experiment is also 1, 2. So there are two experiments, there are two designs which has the combination D1, E2, same thing. 2, 1, 2, 1, this one, and 2, 1, that one. The last one, 2, 2. 2, 2, 2, 2, this one, and 2, 2, this one. DE, 2, 2, that one. So you can finish the combination for interaction DE. In the past, you can draw the interaction plot, right? And we can change the scale in case you want to make it a little bit much bigger, since the range only between 12 to 20. So if the range is too big, we don't need to start from 0. We can start from, say, 10 or 12. So we'll make this figure much easier to determine whether they are interactional or not. So from the interaction plot, is there any interaction for DE? DE, does DE has interaction or not? Xu, DE, does DE has significant interaction or not? No. Why? How to determine whether DE has interaction or not? Okay, you can use Chinese. OK， 假如现有交叉，那个是有交互作用，没错，而且它是哪一种交互作用？对，反向。How about what does it look like if there is no interaction? Yes. If they are parallel, which means that DE has no interaction. So these two lines is not parallel, but very close to parallel. So you will say that even though there is interaction, the interaction will be very small, right? Do you remember how to calculate interaction? We calculate what is the difference between this and that, right? So if you make a parallel line, you will see the difference only this big, which is small. How do you determine this is big or small? You need to compare with the difference between these two. Okay, this and that, compare to that, you will see it's small. But this is qualitative, very 定性上的判断. They are not very parallel. They are not parallel, but only a little bit interactions. That is the reason why we need to use ANOVA. ANOVA can give you a number to determine whether this interaction is significant or not, or important or not. Therefore, how to calculate, this is the interaction plot, but how to calculate the sum of square? Okay, this is how we calculate the sum of square for L8, right? And the original equation is this one. But because L8, we can know what is the Q and what is the level. So you substitute that into the number, but we can also still start from this equation. This is how we calculate the sum square due to the interaction AB. Similarly, you can see this will be sum of square for the average for the combination, right? So there will be sum square for these 4. Multiplied by how many repetition? Q is number of observation in to calculate this average. We know there are 2 design, which is in D1, E1, right? This is how we calculate this average. Therefore, this Q will be 2 multiplied by 2. So sum square for these 4 multiplied by 2 and minus the total average, y bar square, multiplied by n. N is number of experiment in that orthogonal array, which is 8. Then minus sum square due to A, which is already up here, and sum square due to B. Then we can get due to D and E, because we are calculating interaction DE. So you minus sum square due to D and E, you will get the interactions. Let's go back to here. So it's not that difficult. First, we need to determine what is the degree of freedom for DE. What is the degree of freedom for DE? Then, what is the degree of freedom for interaction D and E? J? what is the degree of freedom for interaction dE? Here, what is the number here? 2 minus 1 multiplied by 2 minus 1. Yes, Ian know that degree of freedom will be 1. Okay, looks very carefully on the screen. 1. What changed? The degree of freedom for error changed. It was 2, right? Now it only have 1 degree of freedom. Change from 2 to 1. Why? Because in this model, in the new model, to estimate, if you want to consider, the model will become y mu plus a, b, c, d, e, and what? The interaction d and e. dE. You have one additional effect in your model. You have one additional effect in your model. And for two-level, the degree of freedom for two-level factors, the degree of freedom will be 2 minus 1 multiplied by 2 minus 1, which will be 1. So in your model, it was total degree of freedom it was 7, right? Which is 8 minus 1. And in your models, the main effects already use 1, 2, 3, 4, 5, 5 degree of freedom. And you need additional 1 degree of freedom for this interaction. Therefore, your error, the degree of freedom for error will be 7 minus 5 minus 1, which is only 1 degree of freedom. Okay? So you have to be very careful. When you increase your model, ANOVA for A, B, C, D, E, and also interaction DE, your total degree of freedom remains the same, which is 7. However, because you need 1 degree of freedom for interaction DE, the error degree of freedom will be reduced to 7 minus total degree of freedom used in your model, which is only 1. If you use your equation correctly, the mean sum of square will be this divided by the degree of freedom, which is different, right? Now it's different from our previous model. All right, then how about sum of square due to the interaction? The sum of square due to the interaction now has to be calculated from here, which is, so the degree of freedom for error will be changed too, right? The degree of freedom for error is changed from 2 to 1. The sum of square due to error has to be changed too, because you need to calculate the interactions, the sum of square for interaction first before you calculate the sum of square for error. Because sum of square for error will be the total sum of square minus the sum of square in your model. Because you increase 8D interaction E into your model, your sum of square will be changed after you find out what is the sum square for the interactions. So here, let's calculate the interaction, which is, if you still remember the equation, if not, let's look at here. Q, which is 2, right? 2 multiplied by sum square. What? This combination. Sum square for this 4 combination. And then minus the number of experiments will be 8. 8 multiplied by the total average. 8 multiplied by the total average square. Okay, let me copy the equation over so you don't need to look back and forth. This is here, okay? This is equation like here for two-level case. This is only for two-level case. Okay, so let's do that again. Sum square due to the interaction, we haven't finished that yet, right? So it will be 2 multiply the sum square for this combination. Since we are calculating DE, so we calculate the combination for DE square and minus total number 8 multiplied by total average. After that, we need to minus sum square due to A and B. Then we continue to, it doesn't matter if you want to add a quote or not, but let me add a quote so it'll be clear. Minus sum square due to A, which is, I'm sorry, not A, sum square due to this interaction, D and E. So you have to minus interaction D and minus sum square due to the E. All right, so this will give you the interaction for DE. Any questions? The answer should be 0.0572. Then we can finish that. As you can see, the sum square due to error will be changed as well. If you did the equation correctly, you'll see the sum square due to error will be calculated by total sum square minus your model. Now your model has increased to include interaction DE. So not just A, B, C, D, E, you have to minus the sum square due to this interaction. Then you can find out what is the sum square for error in this case. 0.180. It's different from our original equation. Then you can calculate the mean sum square for this interaction as well. The mean sum square is equal to the sum square divided by the degree of freedom 1, which is the same in this case. Any questions? Okay, let's go back to the PPT. And if you look at the PPT already, you will find out this is what we show you in the PPT. Let me switch to, all right, switch to this one directly. So let's make a summary for what we just did. How do we calculate the two-factor interaction, sum square for two-factor interactions? So this is the equation. Okay, and what does that mean for this Q and, okay, this can be simplified into this. These are the same, can be simplified into these equations. And where Q is the number of combinations, I should say number of repetition when you calculate this average in this interaction combination. So using the L8 example, all right, so this is a summary, okay, sorry. So this is a summary for the sum square due to interaction A, B. If they are due to some other, in our case, DE, you need to change DE. And here, the mean sum square is the sum square of this interaction divided by the degree of freedom. And the degree of freedom for AB is the level -1 minus by the level -1. Let's use L8 as an example. Just like what we did, the equation can be simplified into that. This is only for L8, remember, only for L8. Don't use this equation in three-level design, such as L18. They will be totally different. So here, in this case, the repetition will be 2 when you calculate the average, and the total number is 8 in orthogonal array. And because this is interaction AB, you need to minus sum squared due to A and sum squared due to B. Okay? And when you calculate the mean sum square, because the degree of freedom for this interaction only 1, so mean sum square will be divided by 1. How to calculate that? We, just like what we did before, we first need to calculate the combination of AB. When you want to analyze the interaction AB, this is how we draw the interaction plot, right? So here, when we calculate the sum squared due to this interaction, which is very similar to the main effect, we calculate the difference between each combination to the total average. And we make a square, sum it up. This will be the total sum square, right? Total sum square for the difference between these two, all right? So this can be used using Excel equation, sum square of these 4. So we don't need to type each equation, we just select this 4. Then we can get the result. And how do we put that in the ANOVA table? And this is the confounding structure, as I mentioned before. Before do the analysis of this interaction, we have to find out the confounding structure. This is the confounding structure we just did. And here, DE confounded with AB. So if you want to analyze DE, right, and they are all total 10 combination, right? They are total 10 combination. So if you want to analyze DE, you have to make sure first AB has to be negligible, right? And how do you get this confounding structure from? You can use interaction table. So here, as you can see, this interaction has to be negligible, right? Why this has to be negligible? Because they are confounded with main effect. AC, right here, confounded with D. AD, confounded with C. So this interaction has to be negligible in order to make your main effects to be estimable. Same thing, these two confounded with each other. So only one can be estimated. So before you do the interaction analyze for DE, you have to make the assumption that AB is negligible. Here, your model become, as you can see here, your model become a little bit more bigger to include the interaction DE. So therefore, the sum squared due to error and the degree of freedom due to error will be changed, will be different from our previous one. And this is the result using the Excel. Okay, if your Excel result is the same as this one, then congratulations, you know how to calculate the sum square due to the interaction. Any questions? 有问题举手啊，我可以过去协助各位。关于到这边为止，啊，假如问题的话，助教也可以过去协助一下。Any questions？ 关于交互作用的自由度以及 sum square 的计算，还有整个 model 的改变，有没有什么问题的？有没有问题的？好，没问题的话 ，if there's no questions, then okay, no, this is the same. All right, and now we want to calculate the net sum square for the main effects. As I introduced already, when you calculate the sum square for each main effect and the interaction effects, which also including some error. From our previous analysis, the error can be estimated using this one, mean sum square. This is the error term, okay? So we can use this one as a criteria to determine whether these effects are significant or important or not. If this value is smaller than that, you can see these effects are not important. So Takuchi proposed a net sum square, 净平方和. net sum of square. And the net sum of square is very simple. The calculation will be the original sum of square. Okay, this is, let's look at the equation directly. The original sum of square minus the degree of freedom for this effect multiplied by mean sum of square. And this is called net sum of square. The concept is very simple. As I mentioned before, this sum of square, what is the net sum of square? Which is the original sum of square minus the error. Because when we estimate this sum of square, we use 1 degree of freedom. So we have to minus the error. The error for each 1 degree of freedom, the error will be 0.18. This is mean sum of square. Then 0.008 minus 1 multiplied by that will be the net sum of square. Okay? So basically, this is the equation we are going to use. So here, when we calculate, we can use this one to calculate the net sum of square. Let's go back to the Excel again. So how to calculate the net sum of square? Net sum of square, all right? We can apply the equation directly. The net sum of square by using the equation will be the original sum of square minus the degree of freedom and multiply by the mean sum of square due to error. Okay, this is the equation. Original sum square minus the degree of freedom for this effect multiplied by the mean sum of square due to error. Because our degree of freedom for A is 1, so only minus 1 degree of freedom for this mean square error. If you are 2 level, if you are 3 level in your design, the degree of freedom will be 2, which means that you will have 2 comparisons in this sum of square. Therefore, you need to multiply 2 times of this mean sum square. Okay, let's show you the example later. Any problems to calculate the net sum square? All right, this is minus. For this one will be equal to this one minus the degree of freedom multiplied by this one. In order to use the equation, I will just use $sign to fix this mean sum of square, okay? Because this mean sum of square will be the same. So if I fix it, I can copy this equation downward. Enter. And copy this equation downward. Copy. And paste. And we can double check for the interaction. The net sum square will be the original sum square minus degree of freedom multiplied by. All right, let's look at the term. What is sum of square? 这叫平方和。Remember, square, 平方和, which means that this one will be always because it is a squared number, it has to be positive. Therefore, if it is unreasonable, 不合理的, 负, okay, there is no negative sum of square, 没有负的平方值. So, if there is a negative sum of square, which means that this one doesn't have a sum of square. 讲中文就是假设负的平方和，意思就是它没有正的平方和。所以负值有没有意义？没有意义的。在这里，假如它是负值的话 ，if they are negative, is meaningless to put minus 0.1. You can only use minus to represent that. This is a minus negative, a minus square value. Okay? Don't put it minus 0.013 since they are always positive. Okay? If it is a negative, you don't need to put a number, just put a sign here. Means that the sum square of A is smaller than 0. If it is smaller than 0, it is meaningless to compare. 就跟你的秤的误差是正负5公斤，那你任何小于5公斤的数字是没有意义的。So any number smaller than 0, which is meaningless, which means that effect is negligible, is meaningless. Using your experimental design, you cannot determine the effect of A is similar to 0. If it is similar to 0, it is negligible. So we'll come to the error pooling. What is error pooling? If any effect, main effect or interaction effect, if there is no net sum square, if there is no net sum square, which means that their effect is smaller than 0, then the effect is negligible. It is negligible. If it is negligible, the sum of square and degree of freedom can be pooled into error. The degree of freedom and sum square can be pooled into error to estimate. And this is called 合并误差 pooling. And so we can first delete that effect and add the sum square into the sum square due to error. Same thing for the degree of freedom. We can also add the degree of freedom for this effect into the degree of freedom for error. All right, so let's come back to, so once you have this result, you will find out that the main effect A is negligible since it has no net sum square. If there is no net sum square, you can erase or remove the model, right? Remove the model. Before I continue, I want to make sure you know you have already finished this result. So please, okay, please make a screen copy of this file. At least you need to including this one and this interaction plot. Make a screen copy of this file and post it into Zooview. So I will know that you already know how to do that. Since next we are going to modify the analysis of mean, or the ANOVA table, and then it will become different. 所以主要的就是在这一部分，我知道你 ANOVA 会做，净平方额会做，然后交互作用的这个计算会做就行了。好，那正如同我刚一开始跟各位提到的原本我们的评分方式包含了期末专题报告的这个项目但因为那个我们把那个什么那个时间的关系把这个项目取消掉，所以这 10% 我们就要做一些区分做一些区分。那我就把它稍微调一下因为上礼拜的直升机的报告坦白讲是比较复杂的不是单纯的只有像我们平常练习像打一打就上去了所以把它并到作业里面好像有一点不成比例，所以这里的话呢我就把它改成说这个期末专题部分我就把它改成是直升机它的专题，但是它比例没有办法占到那么高我们就把它恢复到 5%， 然后在这里的话呢 25%意思就是期中跟期末考的比例是一样的，都是 25%但是它的直升机那个专题就独立出来计算它那份报告的成绩我们就把它独立计算，因为它还有做的是直升机花时比较多独立算 5% 的报告成绩，这样可以吗？这样可以吧？好，这种调整 否则应该是要让各位再去做一篇看论文的这个报告的话，但是下礼拜就期中考期末考没有时间，我们就改成这个样子，有没有问题？先跟各位做一个宣布。同样的，这些成绩应该都是先前都讲过的哈，都没有任何变动，就这一项，我们把30% 原本期末考包含的报告部分，把它拆成这个直升机专题跟这个部分啊。So if, as I mentioned earlier, if there is no net sum of square, then we can pull manifold A into arrow. How to pull that into arrow? Basically, is to remove this from the model. Okay, this is the reason why I want you to send a file. I will suggest you to save this file using another name. All right. 把它另存一个新档，把原来的档案留下来，因为我接下来开始要改。All right. If you want to change your model here, we want to do the analysis of mean ANOVA for only B, C, D, E, and also intention DE. Then basically is to remove this one from the model. Okay, I select that and delete. Since the equations are typed correctly, the arrow degree of freedom and arrow sum square will multiply automatically. What does that mean? Let's undo. Okay, when I have A, the degree of freedom only 1. Sum of square is 0.18. When I delete manifold A, see, the arrow become 2, and the sum of square become 0.26. Let's go back, which means that this 0.08 sum of square will be combined or be pulled into the arrow sum of square. So 0.18 plus 0.08 will be the new sum of square for the new model, all right? 0.26. And the degree of freedom was 2. The degree of freedom was pulled into arrow as well. So the mean sum of square will be modified automatically. Will be changed to 0.26 divided by 2 will be 0.13. But if you didn't type the correct equation, the number may not be automatically updated. Now let's look at the net sum of square. The net sum square is different too. Let's go back, Control Z. You see, the net sum square was 0.87, okay, etc. But when I remove A from the model, you see, the net sum square will change. Why? Since the net sum square is automatically calculated from the sum square for the current value, which doesn't change, minus degree of freedom multiplied by mean sum square. So the mean sum square change because we pull the arrow A into the arrow turn, put the effect A into the arrow turn. So the degree of freedom and sum square will change. Then the mean sum square will change too. Then the net sum square will become all positive, right? No negative net sum square. Once, any questions? Very simple, right? When you simplify the model, will be looked like that. And now we want to calculate the contribution percentage. But remember one thing, the contribution percentage only can be calculated only there is no negative sum of square. Okay, no negative net sum of square. The percentage, this one will be the, see, net sum of square divided by total sum of square multiplied by percentage. This is the calculation of the percentage combination, percentage contribution. Okay, any questions? The percentage combinations percentage contribution will be the net sum of square divided by the total sum square. But only the red word here, only if all the effects has a positive net sum square. All right? Which means that there's no negative sum square before you calculate the percentage. If they are negative, just like a previous case, if there is in the previous case, there is a negative sum square, you cannot calculate the contribution right now because it is incorrect. 因为这个负值被分到别的地方去了，意思是这些 sum square 是被过度估计的。Okay, so don't calculate the contribution when there's a minus. But after you pour this negative sum square into the error term, now every net sum square is positive, so we can calculate the contribution. Okay, the contribution here for B will be equal to this divided by total sum square, this one. Okay, enter, and you can make it, okay, let's fix the total sum square first. Then you can copy the equation downward. And this is not percentage, right? So you can change that into percentage by click this one. Click here, you become percentage, and you can increase the decimal into 1 decimal. So you can see 3.2% and 51.5%. And the result should be the same as your lecture notes. Any questions? Very simple, right? Very simple. Very straightforward. But the only thing you need to remember is you cannot calculate the contribution when you have a negative sum square. Okay. All right. How about the contribution for error? The contribution for error is calculated differently, just like what we did before. The percentage will be 1 minus the summation of your model, the contribution of your model. Oh, sorry. Equal to 1 minus the contribution for your total model. Right? It was 100%, and this is the percentage used to contributed by the main effect and the inheritance effect. Enter. So we can see, again, we can make a percentage of 3.2%. And this is the same as page 372. Any questions for the contributions? So, originally, you can stop here. This is a typical analysis of mean, and here we simplify the model to neglect those models need to be neglected. All right? If it has negative sum square, it has to be neglected and pulled into the error term. However, if you want to simplify your model, you can continue to simplify the model, B, C, D, E. Right now we have 4 factors. We can simplify into maybe only 3 or 2 factors, right? And also we can consider whether this interaction is important or not. Okay? How do you estimate whether these effects are important or not? There are some rules. Takushi proposed here, there are some rules. Okay, this is how we calculate it. This is an example, we already did that, all right? This is the error percentage, 3.2%. Now, let's continue to simplify the model. Right now, the result is here. So here, we can look at our table. And you can see that the contribution of error term is 3.2%. And you can see factor B, factor C, and also interaction DE, they have smaller contribution than the error term. So you can consider, 你可以考虑，没有说一定要。So you can consider to pour this effect into error term as well. You can consider to pull this into the error term. See, B, C, D, E has low contribution when you compare with the error. So they can be, not has to be, not has to be. 不是一定要，是可以被。假设你要简化你的模型的话 they can be pulled into error term, just like what we did before. And you can start from the smallest one, change one by one. Because whenever you delete one effect in your model, your ANOVA will be changed. All right, so here, if you remove everything at once, okay, let's use that from the Excel. Okay, this is your model, all right? So again, from here, if we want to remove some not important factors, okay, not important factors, let's start from the smallest one, C. C can be neglected, 0.14. If we remove that from our model, see here, if we remove this, okay, oops. If we remove C from our model, then our ANOVA will become, let's delete that, will become this. Okay, will become this. All right, let's look at the model again. You can see, well, from here, our error percentage become 4.2. Now you can see the interaction DE is not important, right? Compare the contribution of error is small. Same thing for B. So you can consider to remove the interaction term. So this is how you determine whether this interaction term is important or not. From the figures, you can only look at the parallel or not. 你可以只能用平行线从图来看，但现在就有个数字贡献比例让你当做标准。If the contribution is low, if it is negative, it has to be removed. If it is small, you can consider, which means that their interaction is very small, can be pulled into the error term, or you should say it is negligible. Let's remove this interaction again to see what happened. If you remove this interaction, then this one is removed. Your model become B, D, E, only 3 effects. And again, you see the error degree of freedom will be changed from 1 to 2 to 4, 3 to 4, because the total degree is 7, and your model only have 3 degree of freedom, so the error will have 4 degree of freedom. Same thing, sum square will be the total sum square minus this one. This is a sum square for error, mean sum square, and this is the net sum square and the contribution. Okay? From here, you can consider to neglect B again and make your model to be very simple into 2 effects for only D and E. Okay? Remove your model and make only D and E in your model. And when do you stop? As you can see, the error percentage become 10. Can you continue to simplify the model? For instance, well, because these two are already bigger than the error. Basically, you can stop here. If you continue, there will be some mistake. What does that mean? Means mistake. If you say remove D, what happened? Well, error is bigger than E, which means that your model is meaningless. If you use a model with only one effect E to estimate your output, it can only tell you 43% of the output, but most of that is in the error, which means that your model is not good enough. And let's go back. So whenever your contribution are all bigger than error, and also your error percentage is smaller than 15, percentage, then your model is good enough. You don't need to continue to simplify the model. So let's go back to the PPT. So once we finish that, our model simplified into only 2 main effects. But even though we only consider 2 effects, the model is good enough. Because when you add more effects, actually these 2 effects already explain 90% of change. So all the output, by only consider D and E, you can explain 90% of the output. Only 10% were due to the error, which means that in your model, D and E are important effects, and rest of them can be pulled that into error term. All right, so in summary, in the first step, we pull A into error term because there is no negative, right? And next, we simplify that into only 2 effects, right? It was 3.2% for the model. But after we simplify, the error percentage is 10%, which is still small enough. So the second simplify, we consider only 2 effects to explain the model. So you don't need a complicated A, B, C, D, E, and interaction DE. You just need to consider DE. You can control 90% of the output. And here, if the pool percentage is less than 15%, the simplified model can good or well explain the output, the variation of the output. Summary. All right. First, when you analyze the main effect and the interaction, interested interaction, you have to make sure that this interaction can be estimable. 就像我们刚刚讲到的，这个你要分析交互作用，必须先确定交互作用可以被分析的。假如它跟主效应交弱，那个交互作用是不能被分析的。假设它是跟其他交互作用交弱，那你必须确保这些交弱里面只有一个可以被分析，另外一个是可以被忽略的。这是假设。Right? This is what we did that before. And you can pull the error by consider the contribution. Once you have no negative net sum of square, then you can calculate the contribution. If the contribution is smaller than the error, we can consider pull the degree of freedom and the sum square into the error term. Okay. So there are 2 criteria. The effect with no net sum square can be pulled into error, or the effect with a small contribution can be pulled that into error. This is 一定要. This is 选项. All right. And finally, if the final contribution of the error is smaller than 15, we can see this design of experiment is reasonable and your model, 你的模型, 你的加法模式 is good enough to estimate the output, which means that it's good enough to find out what is the optimum design. Because we are using the experimental design to find out what is the optimum combination, right? And even though in this case, we only consider 2 effects, we can still have a good, we can use a small experimental cost, but come up the optimum design. 但是 if the error percentage is larger than 50%, then your model is no good. All right? If your error percentage is larger than 50%, then your model failed to explain the output. 你的模型是错的。那你的最佳设计推论出来80%也都是错的。什么原因呢？ Some important effects may be missing. Maybe some main effects, maybe some interaction effects. you didn't consider, or there are interactions you have to redesign your experiment. OK，F test 这边我就省略了，好，有兴趣的同学可以自己去看。